Okay, so this is chapter 1, section 1, and depending upon the book you're using, it should be graphs of equations. So we're going to talk about graphing equations and what's usually involved. Hopefully most of this, as it says, will be a review. So we've looked at things in the past. Algebra 2, you have probably plotted lines and parabolas. And those are the main two things that you probably have plotted. And so basically what you're doing when you're plotting a graph is you have, let me just put up a page here. Let's find some graph paper. So here's a piece of graph paper, and we label one of the axes x, which is our independent variable, and y, which is our dependent variable. That's just arbitrary choice of those letters to represent the independent variables. And then you'll have some kind of functional relationship. So for a line, you'll have y is equal to something that looks kind of like that. So the question is, how do you plot a line? So there's a couple of ways you can do it. One is you can just create a table where you have x and y values, and you could just arbitrarily choose which x values you think might be appropriate. For a line, you're probably going to choose values of x that are within the limit of values that we're looking at on the graph. Wouldn't make much sense to go outside of that. So let's assume that each grid mark on the graph is worth 1 unit, and we'll do that in both directions. So we go from -10 to +10, -10 to +10 in the y direction. So you can put x, the x variable, y is in that column, and you can pick stuff. So I could pick I could pick -10, say -5, 0, 5, 10, and then I can plug those values of x into this equation. And what you'd find is if you used x equals -10, you get 2 times -10 minus 2, which would be -22. -5 plugged in there, you'd have 2 times -5, which is -10 minus 2, that's -12. Put 0 in, you get -2. If you put +5 in, you get 5 times 2, which is 10, minus 2, which is 8. And put 10 in there, you get 20 minus 2, which is 18. Now, if I went to plot those points, I found out that except for 2 of them, they're outside of the window. So the ones that are inside the window would be 0, -2, which would be this point, and 5, 8. So 1, 2, 3, 4, 5, 8 would be up here. And so that actually would be sufficient to draw a curve. So we could, knowing that a line can be defined by 2 points, and I'm just putting in it like that so I can hopefully go over here and then kind of correct it. So just because of the software I'm using, I kind of have to go back and forth. So, there's the equation for the line. I could have gotten some intermediate points by realizing that maybe I should choose other values of x other than -10, -5, because those -10 would be way down here, and -5 would put you there probably, and so forth and so on. So sometimes it's difficult to decide which x values you need to get the y values that you're looking for. I could change the limits on y to make these fit in there. Sometimes you do that as well. Now there's another way that you can draw a line, which may be easier, in that you'll notice that this line here intersects the x-axis at x equals 1, and the y-axis at y equals -2. So if I found those 2 points, that would be sufficient to then draw a line through them, and I could extend that out either way symmetrically. So a lot of times the x and y intercepts are important in sketching any kind of graph. That's if they do intersect the x axis or the y axis. Now, functions always intersect the y axis somewhere. Well, that's not actually even true. Most of them intersect the y axis. Intersect the x-axis, may or may not. So sometimes you may not have an x-intercept, you may not have a y-intercept, but that's usually the first thing you try. So let's talk about how do you find the x and y-intercepts of a function, and what are the x and y-intercepts of a function? Well, the x-intercept is the case where the y-coordinate is equal to 0, and the y-intercept is where the x-coordinate is 0. If we go back to this graph, you'll see here that's the x-intercept. That's the intersection between the x-axis, which is the same as y equals 0, and the curve. Now the y-axis is also the line where x equals 0. Anywhere along this line, x equals 0. So we use that definition, those two facts, to be able to figure out what the x and y intercepts are. So let's go back to the problem we just did. So if I want to find the x-intercept, I'm going to set y equal to 0. So I'll go to my equation. Instead of y, I'll put in 0. So if we got to write the right equation down first here. So if we solve this for x, what you're going to do is move this to the other side. It becomes positive 2. Divide both sides by 2. You get x equals 1. So the coordinates of the x-intercept are x equals 1, y equals 0. So there's a couple of ways of representing. You can give the x value as the x-intercept, or you can give the coordinates. If we go back and look at this, that's this point here. X equals 1, y equals 0. So that's the x-intercept. Now, the y-intercept, you set x equal to 0 in the same equation. So instead of setting y equal to 0, we're going to set x equal to 0. 2 times 0 is 0, so you get y equals -2. Or you can say it's the point x equals 0, y equals -2. So that's the y-intercept. And again, go back to this graph. You can see that's this point. X equals 0, y equals -2. And then plotting those 2 points, the x and y-intercepts, then that gives you 2 points you can draw a line from. So that's, for linear equations, that's pretty simple. And if you remember back, this is what's called the slope-intercept form of the linear equation. So in the slope-intercept form, you solve for y, and everything else is on the right-hand side. The coefficient in front of the x term is the slope, and this is the y-intercept. So we can actually look at the original equation and figure out what the y-intercept is. It's always this constant term. We did that here. That term goes to 0. But the same procedure applies for non-linear equations. So we're going to look at a few non-linear equations, I think. Now, before we do that, here's an example of a quadratic equation, y equals x squared or minus x squared. And you can see that it does have a y-intercept, but it doesn't have an x-intercept. Now, here's an example of a third-order equation. So this is going to be second-order equations, or something like y equals ax squared plus bx plus c. And depending upon the coefficients, you may or may not have x-intercepts. You'll always have a y-intercept. Same thing's true here for a third order equation. That'd be ax cubed plus bx squared plus cx plus d. So again, depending upon the coefficients, we may have 3 x-intercepts, like here, 1, 2, 3. We'll always have 1 y-intercept. Or we may have 1 x-intercept. Let's see if I have that on the next slide. No. So let me just draw another function here. So let's say it would look something like this, but instead of coming all the way down there, it would like that. In this case, we have one x-intercept, 1 y-intercept, but not 2 additional ones. So for second order equations, we have either 2 intercepts or 0 intercepts. For a third order equation, we have either 1 or 3 intercepts. It's always an odd number. We never have 0. It always has to at least intersect one place. So in this case, the intercept, because there are none, doesn't help us plotting the graph. It does tell us if there's no intercepts, we know that it doesn't go all the way down. That at least gives us some idea. Now here we have a circle, and a circle is actually not a function. So you might have something like x. Let's say in this case we'd have 1, 2, 3, 4, 1, 2, 3, 4. So it would be x minus 4 squared plus y minus, minus 4 squared equals, and the radius is 2, so that's going to be 4. So that would be the equation of this. It's not a function, because if we draw vertical lines here, we get 2 values. It's not a function of x. It's not a function of y. Now, if you looked at just this part, this half, that's a function by itself, and this half is a function. So you could, you can have intercepts of a circle with the axes, but you'd have to first break it up into 2 questions. For example, like this, you'd have to break it up into an upper part and a lower part that were both functions, and then you could solve for the values of x, where that went to 0. We're not going to worry about that one. We're going to concentrate on linear equations, quadratic equations, third order equations, and right now square roots. So let's okay, so here, let's just put this on the screen. So how do we find the intercepts analytically? Well, we just talked about that. What you're going to do is you're going to set to get the x-intercepts, set y equal to 0 in the equation, find the values of x which make this happen, which for linear equations is easier. For quadratic equation, you'll have to factor. For third order equations, it's more difficult. We're going to do that in another chapter. For y-intercepts, you set x equal to 0, find the resulting y. Most of the time, that's much easier to do. So here's another example of a linear equation. Here's the original equation. To get the x-intercepts, you set y equal to 0. If you just solve for x, you'll get x equals -3. You can see if I plug in -3 in here, it's -3 plus 3, which is 0, which is what I came up with. Now to find the y-intercepts, you set x equal to 0, and then solve for y. So in this case, you just get y equals 3. So that's pretty much a piece of cake. Now here is a quadratic equation, and again the procedure is exactly the same. You set y equal to 0. So y equals 0, so you end up with this quadratic equation equal to 0, and then in this case you can factor it by observation. So if we're lucky, that'll happen. And so there are 2 ways this product can be 0. I could have 0 times a, or I could have a times 0. So just if this factor is 0 and this is non-zero, then product of 0 times the non-zero is 0. 0 times the non-zero is 0. Non-zero times 0 is equal to 0. So what you do is you'd say x plus 6 equals 0. So what values of x does this go to 0? So you solve for x, you get negative 6. And then the second part, the second factor, if that's 0, then the product is 0. So if you solve for x, you get 3. So those are the x-intercepts. There's 2 x-intercepts. From a y perspective, to find the y-intercept, you set x equal to 0. So you could either do it in the factored form, or you could put it in there. And what that does is just leaves the constant term. So these drop out. If you put it in here, what would happen is 0 plus 6 is 6. 0 minus 3 is negative 3. You multiply this, give you the same answer. So it depends whether this thing's factored first or not. So that would be the y-intercept. Now let's make a piece of graph paper. Just see what we know so far. See if we can figure out what's going on. So if we take a piece of graph paper here, plot what we know for this last function. So we've got an x-intercept at negative 6, which is going to be here. 1, 2, 3, 4, 5, 6. We have another x-intercept of 3. And we have a y-intercept of negative 18, which is way down here. So what I can do is I could change the scale from negative 20 to positive 20. Here I can still do negative 10 to 10. So if I do 0, negative 18, that's going to be right here. So these are my 2 x-intercepts. This is my y-intercept. So quadratic equations are symmetric. So if you'll see that there's 9 units difference between here. So if we go 1, 2, 3, 4.5, the point of symmetry is right in the middle. That's called the axis of symmetry. So we know that the point on this quadratic equation that's along the line of symmetry has to be below this point, just for the whole thing to be symmetric. And we can figure out what that point is, but right now we're just kind of guessing. And then, just a general shape of a parabola looks something like this. So we can draw a pretty decent estimate of the curve. We could always plug in more values of x and get a better estimate, but with 3 points, it doesn't look too bad. So that shows the utility of finding the x and y intercepts. So here it is. This is drawn using the graphing program. So you can see it. The actual negative, the minimum is, it looks like negative 20. The y-intercept is negative 18. The x-intercept is negative 6 and positive 3. So we didn't do too badly. Now another way of finding the x-intercepts for a quadratic equation is using completing the square, which you may or may not have had. So there's really, there's a couple of ways to factor. One is by observation. So you just kind of think about what numbers are going to work, like in the past problem here, where what 2 numbers multiplied together give you negative 18. So it could be one's positive, one's negative. So it could be positive 9 times negative 2. Could be positive 18 times negative 1. So they're the factors of 18. You'd think about what those factors are, and then think about, are there any where the difference between the two equals 3? So you'd get 6 and 3, and you'd say, oh, well, 6 minus 3 is 3, so it's probably 6 and 3. Let's try it. And this is positive, so I have to make the positive one be the larger of the two. So I make this x plus 6 and this x minus 3. And you check it out, and you say, oh, yep, it works. But, this case, it doesn't look like you can observe that. There is something called grouping, which you may be able, what you do is you take part of this and group it with this part and part of it with that, and hopefully you can see something that'll work out. So let me explain how that works. I don't use that much, but if you had this one, x squared plus 3x minus 18 equals 0. So you might say, okay, I'm going to take x squared and I'm going to put some with the x squared part, and I'm going to put some with the so there's going to be an x, something x here, and then I'll have something x plus a constant thing. So if I think about, again, they have to be factors. So if I put 6 here, then to get back to plus 3, I'd have to minus 3 here, and this number is 6 times that number, so if I took 6 times that number, I might get, well, actually I have a negative sign, so it'd be negative 18, something like that. And then what you can do is you can factor out an x out of here, so you'd have x times x plus 6, and you can factor out a negative 3 out of this, and you get x plus 6, and you'd say, oh, I've got the same factor here, so I can combine those two, x minus 3 times x plus 6, because I've got this part plus that part put together, and I factored it. Ta-da! Okay, so that was, some people teach you that way. The third way is completing the square, and we'll actually do that a fair amount because we use that in calculus, completing the square. And the final approach is quadratic formula. And that always works. It's just sometimes it's overkill. You can do it shorter using one of these other methods. Now completing the square is actually, it's easier when this number is even. If it's odd, you can still do it, but it just becomes more difficult. So what I would do is again, what I'm trying to do is I've set y equal to 0, and I've got so this is equal to 0, and what I'm going to do is I'm going to put 3 over, leave a space right there, and let me leave another space, and then say equals 0. So what I'm going to do is add and subtract the same thing to both the same side, because that gives a net 0 change. So if I did plus a and minus a, because these go to 0, it's still the same expression, same equality. So the way the process is, you take this coefficient in front of the x term, divide by 2, and then you square it. So that's 3 squared, which is 9. And so you add 9. You always add this thing. So if you add 9 there, you have to subtract 9 at that point. Add 9, subtract 9. Now, when you go through this procedure and add this number, you can then take these 3 numbers and make it into a complete square, and the number you use is the term in the parentheses. So 6 minus 2 is 6 divided by 2 is 3, so it's x plus 3, quantity squared. And here I have 3 minus 9, which is negative 6. And now what I'm going to do is solve for x. So to solve for x, you first move the negative 6 to the other side, so it becomes positive 6. Then you take the square root of both sides. So the square root of x plus 3 squared is just x plus 3. And here's the key thing. When you take the square root of the right-hand side, you have plus or minus whatever that thing is. So we have 2 solutions, because we have, when you factor, you get 2 solutions. Okay, we subtract 3 from both sides, so we'll get x is negative 3 plus or minus the square root of 6. So there's two solutions. X equals negative 3 plus the square root of 6, and x equals negative 3 minus the square root of 6. That agrees with what we said earlier. If you have a quadratic equation somewhere here, you always have 2 intercepts or 0 intercepts. So we need 2 or 0. In this case, we have 2. So there you go. That's why you can't do it by observation. Let's just do the quadratic equation since we haven't done that yet. So I'm going to go back to here and I'm going to insert something. So in the quadratic equation, it says you have an equation of this form. So our case, a equals 1, b equals 6, c equals 3. The quadratic equation says that the solutions are minus b plus minus square root of b squared minus 4ac divided by 2a. And then you plug in these values from the equation. So you get minus 6 plus or minus the square root of 6 squared minus 4 times a times c, all divided by 2 times a. So if we complete the math inside the square root, you get 36 minus 12, which is 24. So you get the square root of 24. Now if this ends up being a negative number, then that means there are no solutions. But it's positive, so we're in good shape. Okay, so that doesn't look like what I got here. I got minus 3 plus or minus the square root of 6, but if you look at the square root of 24, that's equal to the square root of 4 times the square root of 6, and the square root of 4 is 2, so you get 2 times the square root of 6. So we have negative 6 plus or minus 2 times the square root of 6 divided by 2, and negative 6 divided by 2 is negative 3, and plus or minus 2 times the square root of 6 divided by 2 is just plus or minus the square root of 6. And there you go. And that's exactly what I got, completing the square. Okay, so that's one thing you can do to help draw a graph, is to get the x and y intercepts. You could also use symmetry. A lot of the functions have some symmetry to them. So if I go back to the quadratic equation, this function here, I'm symmetric about a vertical line drawn through here. If I go either side of that line, I get the same value. Over here, you've got symmetry around maybe this point right there. So if I go this way, I get that value. If I go this way, I get that value. This point is the same height relative to this one, except one's going up and one's going down. So you can kind of think that I take this curve, and if I kind of flip it over, so let me just show you here. If I take this, if I kind of sketch this curve right here to about right there, and then I take that curve and I flip it up and down, and then I flip it left to right like that. You see it kind of matches. This piece kind of got lost in the shuffle. So those do have symmetry, and you can use that to help you. Let's go back to the one example here. So I had this y-intercept over here, so I know if I know that's certain distance from the line, the axis of symmetry, I could say, oh well, if there's a point over here, there has to be another point right over there. So that would give you one more point, which would be about right there. If this is symmetries at 1, I'm not sure where exactly the line of symmetry is. So there's x-axis symmetry, which is kind of like the quadratic function. Origin symmetry is something like y equals x cubed. Y-axis symmetry, sometimes there are other functions that do that. So here we have x-axis. Sorry, that was actually y-axis symmetry is y equals x squared. So here's some examples. We'll learn more about this in the second semester, but this is what's called the exponential function. And this is the negative of the exponential function. So you can see that if I look on either side of the x-axis, that I see kind of a mirror image. So that would be x-axis symmetry. And what happens there is that on one function at the same value of x, it has the negative of what the other function has. So if this is plus 3, then this is negative 3. That means these functions have x-axis symmetry. Here's the y-axis symmetry for a quadratic equation that is symmetric around the y-axis. So if I go 2 units, well, a little less than 2 units this way to the right, I go the same distance to the left, and you see they have the same y value. So what you can do is, if you take the negative of the x value here, you come over and you're still on the curve. And here's the origin symmetry. So a point on this function in the first quadrant that has coordinates x, y, there's a corresponding point in the third quadrant down over here, which has coordinates minus y minus x, so you change the sign of both of them. So here we change the sign of x, here we change the sign of y, and then origin symmetry, we change the sign of both of them. And that's what this description says. So in x-axis symmetry, if you replace y with minus y, you get an equivalent equation, or you get a point on the function that's in the same y location, same x location. For y-axis symmetry, if you replace x with negative x, you get the same y value. And for origin symmetry, if you replace x with negative x and y with negative y, you'll get another point on the function, on the graph. And there's stuff about circles. We're not really going to talk about that. So that's it for section 1, talking about graphing of equations. And we just talked about graphing mostly lines and quadratic equations. We'll get into more about that. What we learned was that the x and y intercepts and symmetry are two things that can really help you.